50 kgs. Exactly 50 kgs. Assuming your bathroom scale reads in kilograms. You could just go straight to newtons. It is your weight, 500 newtons. But so to get 51, you did 500 divided by 9.8. Okay? And you got 50 point what? Or is it 51 point something? Do we remember what it is? What the value is?
No, it's 50.96.
50.96, which rounds to 51 kilograms. No, okay. I'm still rounding that to 51. If at rest you let go of the apple, what's it going to do? It's going to fall to the ground normally. Cool. Part B, now you're accelerating upward in the elevator. What's the scale going to read as you accelerate upwards from rest at 2 meters per second squared? It'll be heavier. Do you know specifically how heavier?
I said 61.22 kilograms.
Okay, so if you looked at the picture over here on the left, they actually give us a fair bit of information here. A 2 meter per second acceleration up on a 50 kilogram mass means that F net upwards has to be 100 newtons. So if you have a net force of 100 up, what's the scale actually going to read? It's going to read 600 newtons. Because gravity is pulling you down, and the elevator is being pushed up into you. So the scale is not just reading your weight, it's also reading the fact that the elevator is pushing up into you. So if you look at the scale, it's going to read you as being heavier than you are. If you let go of the apple, what's it going to do? So if you let it go as you begin to accelerate.
Yes.
So you're not accelerating yet. You let go the instant the elevator starts to rise.
It would fall a little bit quicker.
It would. Because it's accelerating downwards at 9.8 while the floor is accelerating upwards at 2. So that's the same as the same as the apple accelerating downward at 11.8. Assuming you're not moving.
It's hitting the floor quicker, but it's not actually falling faster.
Relative to what?
Like actual gravity. Relative to the building.
Correct. Relative to the building, it's not falling any faster. If you ignore the fact that there's a building and you're just, like, we put earmuffs on you so you can't hear the elevator, all you see is the apple now ripping towards the ground. You feel a little bit heavier and the elevator is ripping towards the ground. Well, but no, it's falling relative to what? You perceive it to fall quicker. The building doesn't perceive it to be falling quicker because the building's stationary. But everything is relative to who's observing. Part C, we have constant velocity. What's the scale going to read? Constant velocity upwards. It's going to read 500 newtons. Or that 51 kilograms. If you let go of the apple, what's it going to do? It's going to fall normally, just like it did when you weren't moving. The elevator slows down as it's rising, coming to a stop. Its acceleration is 2 meters per second squared down while you move up. That's a deceleration. What's the scale going to read now? This one didn't run the numbers for us, but it's going to be equal and opposite from what it was before, right? So if we had a 2 meter per second squared up, that was an F net upwards of 100 newtons. 2 meters per second squared down means our net force is going to be what? No, our net force is going to be what? The F net is going to be 100 newtons down. So the scale is actually going to read less. Connor, you're right. it's going to read 400 newtons, 40.81 kgs. And if you let go of the apple now, what's it going to do? As far as you are concerned,
I'll fall down first.
it's going to fall slower because the motion of the elevator gave the apple some upward velocity, and now the bottom of the elevator isn't going towards the apple as quickly. In fact, the bottom of the elevator is coming to a stop. So basically, if you were looking at it from the outside, you would see the apple rise a little bit and then drop to the bottom of the elevator, because the inertia, Luis's favorite concept, is of the apple is cause it's still going up a little bit when you let go of it, looking at it from the outside. So it's going to fall slower. The elevator speeds up while going back down. It reaches its floor, turns around, starts dropping. What's the scale going to read as you accelerate downwards? It's also going to be lighter here because the bottom of the elevator is racing away from you. Well, racing is a relative term. 2 meters per second squared isn't racing anywhere. So what's the scale? You said it's going to be lighter, and specifically, what's the value going to be? Downwards, we have 500. Our net force, we could figure out what F net is downwards. As I accelerate at 2 meters per second squared down for a 50 kilogram mass, that's 100 newtons. If F net is 100 newtons down, and this is 500 newtons down, then what must be my normal force up? Sorry? No, that would mean that this is that would mean this was 100 up, because up would be bigger than down. If I want my if I'm accelerating down, my net force must be down, which means this one has to be bigger than this one. And the difference between them has to be 100 newtons. So it's going to be 400. So it doesn't actually matter which way you're moving. You could be slowing down while you travel up, or you could speed up while you're traveling downward. Either way, the acceleration is downwards, and in both scenarios, your normal force is going to be smaller. So if you let go of the apple now, same thing's going to happen. You will perceive it to fall slower. And now, Connor's question from yesterday comes. The cable snaps and the elevator with you inside begins to fall. You have time for one last physics observation, perhaps. What does the scale read as the elevator is now in free fall? 0. Because you and it are falling at that same 9.8 meter per second squared. If you let go of the apple, what's it going to do? It's going to float beside you.
That is very weird to think about.
Which is very weird to think about. That's it. Those are the elevator problems I have for you. Not a lot going on with elevators. Comments, questions, concerns about any part of this? It all comes back to F net. Which way are we accelerating? That is the direction of the net force. That will tell you which force has to be bigger. That's all I got. We cool? Okay. Then the last lesson out of this chapter is going to be an introduction to inclines. Now, the inclines piece, we are very briefly going to introduce it. You are going to beat inclines to death on all sorts of nasty ways next year in Physics 12. Can confirm. Riley at the back, thank you. But I figure I want to introduce it to you here anyway. A ball sitting on a level surface is not going to roll around. Why?
Force of bounce.
What forces are acting on that object? Normal force which way? Why is it straight up? And how are the normal force and the surface related to each other? They're perpendicular. So if this guy's flat, normal force is going to be straight up. What else is acting on that ball? Gravity. Straight down because gravity is always straight down, regardless of who you are and what you're doing. Assuming you're on the planet, Earth, well, any planet really, gravity is going to be acting straight down. However, we toss the ball on an incline, and this is an incline, and it starts to roll. Why?
You got gravity pushing down on it. Normal force is no longer perpendicular to the floor. So it
Which way is it's no longer perpendicular to the surface it's sitting on. Sorry, no, it is perpendicular to it's sitting on. It's no longer opposite to gravity.
kind of like this. So gravity's gonna, I don't know, gravity overpowers it, man. That's why it pushes down.
Okay, gravity is up and down. Normal force now looks like this.
So it's keeping it up, so it's not going straight down, but it's gravity's overruling it, pushing it down then.
Yes. I'm going to introduce you to a concept here called components. We're not going to do a ton with it, but we're going to do a little bit with it.
Is there gonna be tests on this?
There might be one question on the test with inclines. It's pretty minor. I won't do a lot with inclines, but I'm going to introduce this to you. So these guys are both vectors, yes? We accept that forces, we remember forces are vectors. Think way back chapter 1, talked about vectors and scalars. Okay, so vectors can be broken into something called components. Okay. And these components, I'm going to zoom in here so it's easier for you guys at the back to see. These components, right here in green, these are perpendicular to each other. When I say these, I mean the components. So the components are going to be perpendicular to each other. So what we're going to do is we're going to break gravity up into two pieces because gravity is doing two things. Gravity is a little bit holding the ball onto the incline, yes? So we can think about the piece of gravity that's holding the ball to the incline. The other thing gravity is doing is it's causing it to accelerate down the incline. So what I'm doing is I'm breaking up gravity into a component that is perpendicular to the surface and parallel to the surface because my surface is no longer level. So what we're going to do here is we're going to label these guys. This guy down here at the bottom, I'm going to call this FG parallel because this component of gravity is parallel to the surface I'm on. And I'm going to call this guy here FG perpendicular because this guy, I'll write that a little bit bigger. This is going to be FG perpendicular because this piece of gravity is acting perpendicular to the surface I'm on. Now, what part of FG is equal to Fn? These two, yes. This guy here and this guy here are equal. So now Fn isn't pushing straight up anymore, it's pushing off at an angle. And in this case, how does the Fn from here relate to the Fn here? Which one's bigger? Which Fn is larger? Yes, because the one on the left is equal to gravity, and the one on the right is equal to a piece of gravity, not all of gravity. The components are always going to be less than the force itself. So if you aren't happy with what your scale is telling you, put your scale on an angle. You won't weigh quite as much. Fun fact. So you put your scale on an angle, because scale's not telling you what you weigh, your scale's telling you what the normal force is. So if you don't like what you weigh, you just put your scale on an angle and it's going to tell you weigh less than you do. Life hack, man. Okay, so we're going to draw it again. FG pulls straight down at all times. FG is going this way. FN now is going this way. Because we've got to remember FN. So although FG pulls straight down at all times, FN does not push straight up. Fn is always perpendicular to the surface. And I probably don't need to hound on this as much as I am, but I'm gonna. So we're going to draw one more time here with feeling. We're going to put a little bit more information on here. So we've got FG acting straight down. We've got Fn acting perpendicular to our surface. And now on this one, I'm going to draw in the components again. I'm going to make them pink. So here, I've got FG perpendicular. Here, I've got FG parallel. And now that, when I talk about parallel and perpendicular, I mean as it relates to the surface we're dealing with here. I told you earlier that components for vectors are perpendicular to each other, which means that this triangle is going to have a right angle, and that right angle has to go between where those two vectors are. And I'm pretty sure similar triangles is not part of the math curriculum anymore. Is that true? What, if you're asking me what do I mean, then I'm right.
No, I just didn't.
Similar triangles, is that a thing that we do in math? Okay. So then I can give you kind of a hand-wavy argument for this, but for now, trust me when I say this angle right here, which we're going to call theta,
Oh,
Greek letter representing angles, is going to equal this angle right here. How many of you can see how that could be true? How many of you need at least some convincing? How many of you don't know what you need, but you wouldn't mind some convincing? Okay. How many of you just don't care? Appreciate the honesty. Love it. Here we go. So for those of you who need some convincing, so here's my kind of hand-wavy argument. Okay? So I've got the angle. It's not necessarily, like, you shouldn't just blanketly trust that this angle on the incline is going to be related to the angle here between a vector and its components. Like, that doesn't necessarily have to be something that you take to be just fact. But there are reasons for why that is the case. So my hand-wavy physics argument is going to be this. What's going to happen to this angle as I lower the incline? It's going to decrease to eventually reaching 0. While that's happening, what's going to happen here? As the incline decreases, this angle is going to drop to 0 at the same rate that this angle is dropping to 0. When this one and this one, when the incline is no longer an incline, then there is no FG parallel anymore. Then FG is all just FG perpendicular. And when these two hit 0 at the exact same time, I could make the exact opposite argument. When I raise them together, they're both going to grow at the same rate. And as a result, these angles must be the same. That's my hand-wavy physics argument. I could give you an argument for geometry using angles and stuff, and if you want that, I can happily give that to you. But if the hand-wavy argument is sufficient, all you need to recognize is that these two angles are going to be the same. And just take that as gospel truth and run with it. Are you sufficiently convinced? Okay, if you want the trig, I can give it to you later. So here's what we're going to do. Yes, Manuel.
Define FG2.
FG perpendicular or parallel?
Is that what you're talking about?
This guy here?
Yeah.
Yes.
Yeah. To find that, are you doing percentages?
No.
Can you show us how to do it?
That's what these three examples at the bottom are going to be for. Yes. I am about to show you. Because it's not Pythagoras, because all we know here is FG. Because FG is just mass times 9.8. You are going to know what that angle is in there, because I'm going to tell you what angle the incline is at. In this case, it's 35 degrees. So if you know one side and one angle, you're not using Pythagoras, you're using what? Yep. SOHCAHTOA, you're using sine, cos, or tangent. And I'm hoping by grade 11, we are at least a little bit comfortable with using trig. And if not, I'll review it here right now. So here we go. I've said it before, let's write it down clearly. Only the parallel component of FG pulls down the ramp. The perpendicular component is equal and opposite to Fn. So we're going to do a couple examples here of what this looks like. And then I've got like 9 questions for you to look at. I'm going to assign half of them, because the other half is going to be part of your review. So here we go. An 8 kilogram block slides down the frictionless inclined plane shown. What is the acceleration of the block? First things first, always first things first, free body diagram. What forces are acting on this block? Normal force perpendicular to the surface. And what other force? Gravity. And this is an 8 kilogram block, so we can put a value in for gravity. 8 times 9.8 is going to be 78 point something. 78.4. Are there any other forces acting on this thing? Frictionless. Friction comes in example 3. That's it. So, and thank you for telling me that that was it. In physics 12, my students, we get quick and sloppy. You got to recognize these aren't individual forces. These are just pieces of gravity. So as far as your free body diagram is concerned, this is it. You will, at some point in the future, you'll be given a multiple choice question. It'll say, what's the free body diagram for this object? And it'll have the components listed. That is incorrect. And I'd say that not because you will be given a multiple choice question, and the question will be, which of these is the correct free body diagram for this object? This is the correct free body diagram, because these aren't forces. These are components, and you don't include them on a free body diagram. I'm not going to ask you that question, but you're going to get it next year. I shouldn't say I won't. I might, if you have me for Physics 12. That's definitely a test question I'm going to give you. Here we go, though. So we've got our free body diagram. Now, the free body diagram's complete. We're going to add in those components as such. This is the 90. This is FG parallel. This is FG perpendicular. Now, I want to know what the acceleration is of my block. Oh, and the other piece is, this angle right here is 35 degrees. That guy right there. So, what values do I have to find here? I want to find acceleration. So to find acceleration, I need what? I need FG parallel. Why? Because that's the only piece of a force acting in the direction of movement. Good. So here we go. Let's write this up. Just so we're clear what's happening here. F net equals ma. And the only force acting in the direction of the motion of this block is FG parallel. And that's only true because the surface is frictionless, which you're going to see here in a sec. So FG parallel equals MA. So now I need to find FG parallel. Well, this is a right angle triangle. This should be something you're able to solve relatively easily. If that's 35 degrees, that's my FG is my hypotenuse. How do I find FG parallel? Which sine, cos, or tan ratio do I need to use? That's my angle, and I want the side that is opposite. So which? I need sine, because sine uses opposite and hypotenuse. So sine 35 is going to equal FG parallel over 78.4. So FG parallel is going to equal 78.4 sine 35. So what is that component of gravity? Sorry? Does it cut off at 9.6 or does it round to something? 9.7, okay. So then I can plug this in here. 44.97 equals the mass, which is 8 kilograms, times the acceleration A. So A is going to be 44.97 divided by 8. So my acceleration is going to be, love it, meters per second squared. Which way? Which way? Yeah, which way? Accelerating. Sure, down the incline. Love it. So here's an interesting question for you. I mean, at least I think it's interesting. Does the mass of the object matter? I'm not asking about friction. I'm asking about this question. Does the mass of the object matter? Why? I mean, whenever else gravity acted on a free falling object, did the mass of the falling object matter? No. So does the mass of the object here matter as it gets pulled down the incline on a frictionless surface? Does it? Where did, this 8 here is the mass. I'm dividing by the mass, right? Where did this 44.97 come from?
It came from the angle.
And?
It came from the opposite. We would solve it for the.
Yeah, but okay, so it came from here. The 78.4 sine 30 actually be sine 35. Where did that 78.4 come from?
It came from the parallel component.
No, it didn't. Where did that 78.4? It came from gravity. The force of gravity. So that 78.4 is mass times g. So this 44.97 has mass multiplied by mass built into it, and then I divide that mass away right here. So does the mass of the object actually matter? No, because I multiplied by it here and then I divided by it here. So what we've got here is it doesn't matter what the object on the incline is. If the incline is frictionless, regardless of the mass, it's going to accelerate downwards at 5.6 meters per second squared. That's an interesting result. Perhaps. 2 more. So a similar style of question might be this one. How much force is required to push an 11 kilogram block up the frictionless ramp shown at a constant velocity? Let's talk this thing through first. What is important to pull out of this question? Yes, the answer. Thank you, Manuel. So helpful. Frictionless is important. What else is important? Constant velocity is also important. Constant velocity implies what? Which implies what?
It's the balance going up.
Which means the forces are balanced. What forces?
Gravity and
Not gravity.
or parallel force and friction.
Fg parallel has to equal. We're on a frictionless ramp. Fn isn't going to push anything up because Fn acts at an angle. Here, let's throw this in here. I've got Fg straight down. And I've got Fn this way. Fn has nothing to do with getting that block up the ramp. What other forces are acting on that block?
Applied force.
Sorry, Eric, did you say something? Fa, there is an applied force. We are told that you want to push the thing up the incline. So to push it, there must be an applied force upwards. So in this case, then, Fg parallel is going to have to equal that applied force. So the act of going through all of this at the start is the same, it's equivalent to what we did over here, where we said, okay, well, Fg equals ma, and then we did the calculations at the end. Here, we did a bunch of, we reasoned through a bunch of calculations at the beginning. All I need to do now is find Fg parallel, and we're done. This will be the force required to push this block up this ramp at constant velocity. So now what we can do is we can go through and we can build our component triangle. That's perpendicular there. This is going to be Fg parallel. This guy here is going to be Fg perpendicular. And this angle right here is also going to be 58 degrees. That guy right there. So then Fg parallel, oh, and we could have figured out what Fg was earlier. Fg is going to be 11 times 9.8. What's that value? 107.8. So then Fg parallel is going to be, I want the opposite side from that angle. So, and that's the hypotenuse. So I'm going to use sine again. So this thing's going to be 107.8 sine 58, which means Fg parallel is going to equal what? 91.42 newtons. Which means my applied force is going to equal what? Thank you, Khalil. Up the incline. What's the interesting application here? There's a result here that's really quite interesting. Let's say I want to get a really heavy object up high somewhere. How could I make my life easier? On a question about inclines, you're going to pull out pulleys. What force do I have to apply to get this object up higher in this question? Yeah, I'm pushing upwards at 91.42. If I'd lifted this object straight up, what force would I have had to apply? 107.8 newtons. So by creating an incline that I can push up, I actually am able to apply a smaller force to get the same end result, right? Like I push this guy up the incline versus lifting him straight up. I'm, I guess, gender identifying the box here. How could I have decreased my applied force even further? If I decrease this angle, I can create a ramp that's the same height. I just have to make it longer this way. Then I apply a smaller force to get it up the incline, right? This is really quite useful, assuming you've got really heavy things to move and a relatively weak force in which to move them. I don't know, an application of this could be you want to build a giant pyramidal shaped structure and you need to move 1,000-kilogram blocks of limestone and you've got tiny people. You, my Egyptian slaves, are going to build me my pyramid.
Where's that? Are you allowed to say that?
No, this is exactly what I'm talking about. I am literally referencing the pyramids of Egypt. You, my Egyptian people, are going to build me my Egyptian pyramid. Or can any one of you move a 1,000-kilogram block of limestone? Straight up? No. One. Okay. Really? No. You cannot lift a 1,000-kilogram block of limestone, Riley. You wouldn't be a high school rugby player if you could lift. If you could squat 1,000 pounds, you wouldn't be here anymore. Okay. So a really simple application of this is if you need to move really heavy objects and you need to get them up high, but you don't have the strength to lift them vertically, and they didn't have cranes back when these guys were building these things. They just built gigantic ramps up the side of the pyramid and then pulled all that dirt away when the thing was done. This is one of the simple tools, for lack of a better word. Pulley is another one, yes. Connor pulls out pulleys. There are simple contraptions that are designed to make our life a lot easier when it comes to stuff like this. The incline is a huge one. Okay? They are all of the lever, the fulcrum, the incline, and the pulley are the four that get referenced all the time. But that's the interesting result here. You actually can lift this same object by applying a smaller force than the force of gravity, assuming you're pushing it up an incline rather than lifting it straight up. Interesting result. Okay, last one, and then I will release you to work on some questions here. A 15-kilogram block sits on an inclined ramp whose coefficient of friction is 0.21. What is the acceleration of the block? Okay, free body diagram time. We're jumping straight to free body diagram because it says what is the block's acceleration. If I had said constant velocity, then we would have gone through and we would have made this argument. But because we know it's accelerating, we got to start with free body diagram. Manuel, yes? Not related? Okay. What forces are acting, or what can we draw acting on this block? Fn's going which way? That way? Fg is going which way? Force of friction is going which way? It's going up the incline to the left. Yes, going against the grain, against the way the block wants to move. You got to go, Manuel? No, okay. You just look like you're packing up. Okay, so that's my free body diagram. Let's add to our free body diagram the components of gravity. Here is my FG perpendicular. Here's my FG parallel. This angle right here is 40 degrees. What now?
We do some sine stuff.
Okay. To find what?
The opposite thing.
Okay, so FG parallel is going to be FG sine theta, which means FG perpendicular, which we've never had to find. What is it going to be? If this one uses sine, which one is this one going to use?
Cosine.
Correct, because I'm using the hypotenuse, and now this side is adjacent to this angle. So this one's going to be FG cos theta. I don't have enough room to actually put the values in there, so I'm not going to yet. Force of friction. Formula for the force of friction was mu Fn, which in this case is going to be equal to mu times, now what is Fn equal to? Well, but we have an expression for it already. Fn is equal to what going on down here? Yeah, it's going to equal to the perpendicular component, which we already said was Fg cos theta. Thank you, Manuel, for saying it a couple times. If that sounded sarcastic, it wasn't meant to be. I was actually like legitimately thanking you. So now we can go through, before I even calculate any of these values, what I'm going to do first is I'm going to go plug them into my Fnet equation using, because I want to get you guys a little bit used to seeing not values in my Fnet equation. So Fnet then, I'll do it down here, is going to equal ma. Now, what forces are acting in the direction of motion of my block? Friction. Oh, and which way are we going to call, excuse me, which way are we going to call positive?
Down slope.
Okay, if down the slope is positive, then what is going to go into my Fnet equation here?
Force of friction
Force of friction
is negative.
is negative, and
Uh,
Fg parallel is positive. Yes, good. So it's going to be Fg parallel minus force of friction equal ma. Well, Fg parallel, that's going to be Fg sine theta minus mu Fg cos theta equals ma. Well, Fg is just equal to what? Mg, right? Without plugging any values in there. Are we cool with this? Fg is just mass times gravity. Are we cool with that? Manuel is, but is anybody else? Brendan seems to be okay with that. Cool. So this is going to be mg sine theta minus mu mg cos theta equals ma. This is interesting. I'm doing this because I want you to see one more time. What can I do with my masses here?
you can cancel. No, you can't.
I can. If I divide both sides by m, it's going to cancel the mass out of this side, and it's going to cancel the mass out of both of these two terms. The only reason I can do that is because my mass shows up in both terms. So my masses, boom, 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 are all going to cancel. So what I'm going to get here is that this is going to be 9.8 sine 40 minus 0.21 times 9.8 cos 40 equals A. And the interesting thing here is it does not matter what the mass of that block is. The only thing that matters is what the coefficient of friction is between those two blocks and what the angle of the incline is, because my masses cancel out, which is really cool. I think it's cool. So then what's the acceleration? Grab a calculator and someone tell me what this value is. Sorry? 4 point. I got a smaller value. Maybe I screwed up.
4.72.
Yeah, I got a 4.7 is what I wrote it down as. Cool. So the only time that mass mattered was when? We had friction and mass didn't matter.
Oh,
Second one. The only time mass, and how is this one different than these two? There's one glaring difference between both of them.
acceleration up this one.
Sorry, Connor?
They're both looking for acceleration on the left and right. This one.
These two let gravity accelerate the object as much as we want it to. This one,
This one's all us.
no, it's all you. There's no acceleration. if acceleration, if you want acceleration equals 0, or you want to have control over what the acceleration is, all of a sudden that's where the mass matters. But if you're going to let gravity do what gravity's going to do, now all of a sudden the mass doesn't matter, which is interesting. Okay, here's what I'm going to get you to do. Flip the page. I want you to look at a bunch of these. Like I said, I'm going to assign half of them, but there's 9 questions. How do I assign 4.5 questions?
4.5. How do we do 4.5?
Okay, you're going to have to draw all of these, by the way. I want you to do
1, 3, 7, 9.
I want you to do number 9. No, the reason I'm not assigning all of them is because I want you to save some for the review, because I don't have any incline questions on the review. That's why I don't want you to do all of them. We're going to do 9. We're going to do 7.
Hey.
You're going to do
3 or 5, 3 or 5. No even numbers.
Actually, no, the other ones are really easy. We're going to do 1 and 2. 1, 2, 7, and 9. We'll leave the rest of them for you to go back and look at for when you review. I do. Right behind. Where did they go? Oh, they're right here. In that green box.
Right, the chain I made.
The chain you made. Okay. Now, the other piece is this.
What is that?
These, ladies and gentlemen, are the chapter reviews.
You're awesome.
If you would like to take them now, okay, ladies, give me a sec. Back, give me a sec. If you'd like to take the reviews now, start working on them over the weekend. Here they are. Come grab one. If you will have all day Monday to do this, and some of Tuesday, oh, wait a second. When did I say your test was the double walk? Thursday. Test is Thursday. So Monday is sure. Maybe Tuesday.
You said Wednesday.
So we're good. No. It's the double block. Whatever the double block is your test. Wednesday, we're starting the new unit next week for sure. At the very least, finish the incline homework over the weekend. If you also want to get started on the review, there's a lot there in the review. Class is not over, so you don't have to, pack up and leave. But class is over in 5 minutes, so.
I'm gonna go to the washroom before next fall because I got tests and I'm gonna start.
Yeah, go for it. Okay, so I would like you to start don't get up and move around. Either be in your desk working on this, or, just be in your desk and not doing this. Just don't pack up and go hang up by the door.
Wait, is that?
And do not leave these 4 questions till Sunday night, because that's how you'll forget how to do them. If you're not starting this now, do them tonight or tomorrow morning. Because you'll go back on Sunday night and you'll be like, oh yeah, and then you'll be like, no.
Uh-oh. Late night chat.
There you go. Not a chance. Watch the video.